Quick question. Are you guys playing the talk? Hello. So, good morning. This is the second session of EGPGV. So now we are going to present our speaker, Burlen Loring. He's going to talk about improving performance of end-to-end processing and data redistribution in transit analysis and visualization. So, Borlen, we have roughly about 20 minutes to do your presentation, and welcome to the session.
Great. So I should be talking in Zoom or Discord.
Hello, my name is Brian
Zoom.
and
We are
I
going to do
represent
everything
performance
using
of
Zoom.
end-to-end processing and data redistribution in transit analysis and visualization. We'll begin with an overview of what we mean by end-to-end in transit analysis and visualization. In this scenario, a simulation runs on M MPI ranks, is generating a solution on decomposed set of P data blocks, which are distributed amongst the M MPI ranks. An analysis job is running concurrently on the same HPC system on N MPI ranks, and this analysis job will process the data as it's being generated by the simulation.
So
first, a partitioning step is needed to decide how the blocks
could
will
you
map from
unmute,
the M
please?
simulation ranks onto the N analysis ranks.
Okay.
Once that partitioning decision has been made,
Hello,
data can then
my name is Burlen Loring,
processed.
and I will present improving
So
performance
the research
of
questions
end-to-end
that
processing and data redistribution in in-transit
are the
analysis.
performance characteristics of M2N in transit configurations for a variety of producers, consumers, and at varying levels of concurrency. Second, what are the performance gains that result in an M2N in transit setting when making use of data model metadata to move subsets of a problem domain as compared to moving the entire problem domain from producer to consumer? And finally, are these results consistent across multiple producers and consumers? In the results of our work, we present a design pattern for solving the M2N data redistribution problem that arises in all in-transit processing. We present a description of an implementation and a demonstration of its generality and scalability. Our work includes an in-depth performance evaluation that examines multiple dimensions of performance at large scale on an HPC system, using data generated by a mini-app in an AMR-based CFD simulation. We explore different partitioning strategies and optimizations, and provide some insight into what are the right ratios of M to N to use for in-transit processing. Our studies demonstrate that substantial performance gains can be realized when M to N data redistribution is tuned for a particular scenario. Before presenting our performance studies, we'll go into the design work. Our work extends the Sensei in-situ infrastructure for use in M to N in-transit configurations. In an in-transit mode, we make use of two MPI jobs running concurrently. The simulation generates data and periodically invokes in-situ processing. It's been configured to use an I/O library that can signal when new data is available and respond to requests for that data. The endpoint is a parallel application provided by us, which configures both an I/O library and an in-situ library. The I/O library listens for signals of new data, and upon receiving one, invokes in-situ processing. The in-situ library can fetch new data using the I/O library. The different components of the system are runtime configurable via XML configuration files. This gives the system a great amount of flexibility, and it's something that we need to consider in our design. The Sensei system is based on the adapter pattern. In here, it abstracts two operations, invoke and fetch. Analysis adapters provide the API for invoking in-situ processing and data movement. And Sensei comes with a number of library-specific implementations of analysis adapters for libraries such as Catalyst, libsim, Ascent, Adios, HDF5, and libis. Sensei's data adapter define APIs for fetching data in a standard form. These are used by in-situ library analysis adapters to get data to process. Simulations must provide specific implementations of a data adapter. In the in-transit mode, there's an in-transit data adapter that extends the data adapter APIs with stream control and partitioning APIs. These also have library-specific implementations for Adios, HDF5, and libis. Configurable adapters provide the runtime configurability. These use user-provided XML to select and configure the library-specific adapters to which operations are delegated. A partitioner abstraction defines the APIs for data redistribution. The partitioner presents in in-situ library adapters a view of the data as it will land on the endpoint. It also provides the I/O library adapters a recipe for moving the data when data is fetched. There are a number of default implementations that can be selected at runtime via XML. The default, if nothing is done, is an equipartitioning algorithm. Optionally, the library-specific adapters can install a customized partitioner at runtime. One can use runtime type information to tell if one is in transit mode. Our design extends the data model to include the metadata needed to make partitioning decisions. Metadata should have a compact and yet comprehensive description of the simulation data. It should also be cheap to move around. Our metadata includes 35 fields, including per block, per array, and per level descriptors of the data. In addition, it describes the data's mapping onto hardware resources. For instance, how it's decomposed on the M simulation ranks. It's also used to present a view of how the data will land on the endpoint, and this becomes a recipe for moving the requested data. The performance studies we present later in the talk examine the impact of partitioning strategies on extracts. Extracts are a data reduction method that extracts a feature or geometry and writes it to disk for later analysis or visualization. This reduces I/O costs while retaining some familiar post-processing workflow. Our studies look at slice-based extracts. Our extract can be configured to either calculate a planar slice or a set of isosurfaces and write them to disk. The operations use VTK internally, and cell-centered data is converted to point centering before processing. Our studies are going to examine different partitioning strategies for slice-based extracts. First of all, we have the default, which is an equipartitioning of all blocks. When we're computing planar slices, we can use the per block bounding box metadata to exclude blocks that do not intersect the slice. Those blocks are not needed for the calculation and need not be moved or processed in the analysis job. In the case of the isosurface extract, we can use per block array min-max metadata to determine if an isosurface value intersects a particular block. The blocks not needed for the extract need not be moved nor processed. These optimizations can result in reduced data movement, memory use, and processing costs. Moving on to our performance studies. First, we're going to present results obtained with running a mini app under varying concurrency. The goal of these experiments is to understand extract performance under varying endpoint concurrency and assess the different partitioning optimization strategies. We also want to gain insight into choosing the right ratio of M to N for extract operations. In the experiments, we fix the simulation workload with a mesh size of 4096 cubed cells and always run on m equals 8192 ranks. In the experiments, we vary the endpoint concurrency from n equals 128 all the way up to n equals 8192 in power of 2 steps. During the runs, we measured 4 performance metrics to assess the effectiveness of the optimizations. The simulation is run for 10 time steps, and data movement is done by ADIOS 113.1 FlexPath staging method. The table on the right shows the matrix of runs that we made. In this slide, we present the results of the series of isosurface extract experiments. The slide shows 4 plots, one for each of our 4 performance metrics of data moved, memory used, total runtime, and core hours built. In this slide and all those that follow, we use the same coloring scheme. Results obtained with the optimized partitioner is shown in red, and results obtained with the default partitioner is shown in blue. In these figures, the horizontal axis shows n, the level of endpoint concurrency, and it varies from 128 up to 8192. In these experiments, the mesh size is fixed at 4096 cells cubed, and the level of simulation concurrency is fixed at m equals 8192. In terms of data moved and memory use, the optimizations reduce data movement and memory use at all concurrencies. In terms of the total runtime and the core hours build, the optimizations outperform in the regime where n is much less than m. However, as n is increased beyond some point and approaches m, the optimizations have less of an impact. And beyond some point, the cost of solution starts to increase. This is obviously something we'd like to avoid. To better understand the trends shown in these charts, we've gone back and analyzed the output of the optimized partitioner to determine the concurrency at which there's one block of work per rank. And we're showing this with the gold line. As you move to the right of this gold line, the number of ranks with no work to do doubles with each dot. This explains why the time to solution remains constant while the cost of solution increases. Now, as we move to the left of the gold line by each dot, the amount of work per rank is doubling. And in these experiments, we found that the best result was obtained when there was 4 blocks of work per rank. And reducing the concurrency below that point down to 128, where there's 16 blocks of work per rank, didn't negatively impact the solution, time to solution, all that much, nor the cost of solution. This hints that lower values of n relative to m, where there's some level of oversubscription, are beneficial. In this slide, we present the results from the slice extract experiments. And again, we've got 4 panels, one for each of our 4 performance metrics. Results obtained with the optimized partitioner shown in red, and the default partitioner shown in blue. The horizontal axis again shows the level of endpoint concurrency n, and this varies from 128 up to 8192. Again, the simulation mesh is fixed at 4096 cells cubed, with m equals 8192 simulation ranks. The results are qualitatively very similar. The optimizations always reduce data movement and memory use. The optimizations outperform in the regime where n, the level of endpoint concurrency, is much less than m, the level of simulation concurrency. We see that by analyzing the optimized partitioner output, we can find the level of concurrency where there's actually 1 block of work per rank, and above that the cost of solution goes up, and again, something we want to avoid. Again, we see that some level of oversubscription where there's multiple blocks per rank being processed on the endpoint is beneficial. In this experiment, we did a detailed profiling of the mini-app with the 4096 cube mesh with a fixed concurrency where m equals 8192 and n equals 120. This was our best case for the isosurface extract, and we wanted to find out why it performed so much better and where was the time spent. So we instrumented the code with timings for a series of events that we defined, and these bar charts show the slowest event time across all events and all occurrences of an event. So again, results obtained with the optimized partition are red and the default blue. I'm going to just show quickly through these the total overall difference. These are the data movement events. This is the calculation of the isosurface and writing the extract. Note that partitioning costs are very low and don't contribute substantially to the solution time. This is the one case where the optimized partitioner was slower. Here what was going on was that when we used the optimized partitioner, the extract was running so fast that the call here blocked and we had to wait. Whereas with the default partitioner, the extract was much slower than the simulation and hence didn't block. When it got to this call, data was ready. So this actually indicates a benefit with the optimized partition. So this slide just shows the speed ups relative of the optimized relative to the default. Everything, the overall, we got a 4x speed up, and data movement varied between 3 and 4. Calculation was about 4, and I/O was about 6x speed up. Now we're going to move on to our performance study of a real simulation at scale that uses IMR compressible Navier-Stokes multigrid solver and AMRX-based code. In this series of experiments, we configured IMR to solve the Rayleigh-Taylor instability, which models the mixing of two fluids under the influence of gravity. We set the simulation concurrency at m equals 8192 MPI ranks. We used 1025 KNL nodes on Nurse Cori, and we configured IMR to use 4 OpenMP threads per rank. The total concurrency was 32,768 cores. We set n equals 128 MPI ranks and used 9 nodes. For these runs, we use Audios 2 version 2.5 with the SST RDMA engine to move the data. The level 0 mesh was 1024 squared by 2048, and it's decomposed into 8192 blocks. We set IMR to remesh every 2 course time steps, and there's 1 level of refinement. In this figure, we're plotting the results of the extract. Shown on the left is the isosurface at time step 440. In this time step, there were 18,654 blocks total. In the middle, we're showing the 4,771 level 1 blocks that were needed for the calculation, and the 5,691 level 1 blocks that were not needed for the calculation in the far right. Note that in the far right panel, I have not rendered any of the level 0 blocks because they would occlude all of the level 1 blocks. So we ran the simulation out for 440 time steps, doing an extract every 10 time steps. And then at the very end, when the simulation had evolved into a very complex state, we did a detailed performance analysis of the last 10 time steps. In the panel on the right, I'm showing some data that we gathered during those initial runs from the initial configuration all the way out to time to 440, where I captured the amount of data that was moved. And this shows a substantial reduction in data movement as the simulation evolves when using the optimized partitioner. In terms of the last 10 time steps where we did detailed performance analysis, I've got bar charts comparing the default partitioner in blue and the optimized partitioner in red for our 4 performance metrics. In terms of the amount of data moved on average per time step, the optimized partitioner moved about a third less data. In terms of the memory use, the optimized partitioner used about half the amount of memory. In terms of the time to solution and cost of solution, and again, this only considers the last 10 time steps, there was a 30-minute speed up with the optimized partitioner and a substantial improvement in the cost of the solution in terms of CPU hours. In terms of the time spent per step, first the bar chart on the left shows the average processing time per step across over all 10 time steps. And in this plot, we've got the gray region indicating the simulation time, and the blue and red regions indicating the extract time. The data from which this bar chart was generated is shown in the right 2 panels, where we've captured the simulation time in teal and the extract time in blue and red. And these are stacked plots, so the extract time is stacked on top of the simulation time in both of these. And this shows a pretty substantial improvement with the optimized partitioner. In fact, with the chart on the right, all but the first execution of the extract ran in under 2 seconds. In conclusion, we analyzed different partitioning strategies while computing extracts in transit. Operation-specific partitioning optimizations can be used to reduce memory and data movement and can result in lower time to solution and cost of solution. They can be worth doing, so it's worth investigating and figuring out how to do them. With the optimized partitioning strategies, we got the best result when M, the simulation concurrency, was much larger than N, the endpoint concurrency. This hints that for a constrained M, if you don't know what your N should be, that you should choose a relatively lower value. And to select that value, you can base on memory use by estimating the fraction of data that will be needed in an extract and add some safety factor. Some potential applications to visualization: the way the system's currently set up, we could apply the same partitioning optimizations, for instance with Catalyst, Ascent, or libsim when they were rendering slices or isosurfaces. This would require some coordination. We'd have to make sure that the partitioner was configured to use the same slicing parameters or isosurface values that the rendering library was, but that could be beneficial, and it wouldn't require modifying any of the adapter codes. So furthermore, some of these systems actually implement similar optimization strategies internally, notably Visit libsim. If this was exposed in the in-situ layer, we could leverage that and provide optimizations based on that. So that concludes my talk, and I really appreciate the opportunity to present it to you all. Thank you so much.
Okay, can you hear me now?
Yes, now we hear you.
Okay, so thank you, Burley, for your presentation. So we are in the session of QA session. So I believe somebody is going to ask any questions if they have. So I will guess that the question could be posted in the chat. In YouTube. In YouTube. So, well, if there is no question, I have one question for you. It is mostly a technical question. I see that in the mini app, you were using ADOS 1.5 with FlexPath in communications, and then in the Amrex application, you used ADOS 2.5 with STT. Have you found any differences about using both, maybe in the setup process of the simulation?
Yes. The Adios 2.5 is much better than the Adios 1.13.1. So the Adios 1.13.1 FlexPath. Can you hear me, Benjamin?
Yes, I can hear you.
Yeah, so the Adios 1.13.1 with FlexPath used sockets. And the Adios 2.5 with SST used the RDMA. And it works a lot better. It's pretty fast.
So did you find any limitations between both, in particular when trying to set up your N values? Because I mean, you said that ADOS, that FlexPath uses sockets, but SST uses RDMA. So at some point there should be a limitation, right? Number of connections.
I didn't find that. We actually did fix a bug with Cray. I think it's particular to Corey. The NERSC system where we made the runs. There was some bug in their RDMA system where the server that managed the RDMA to keep the memory confidential to one job, that system that managed that confidentiality wasn't capable of handling all the connections, and that crashed. We worked with Craig to fix that. So other than that, there was no limitations in audio.
We need to.
Okay. Okay, thank you. So, thank you for your presentation. Okay, so now we are going to go to our second presentation. This presentation will be given by Christian Grebel from Applied Technology Operations, Service Engineering. The talk title is Effective Parallelization Strategies for Scalable High-Performance Iterative Reconstruction.
Hello everyone, my name is Christian Gribble, and for the next few minutes I'll be discussing some work we've done to explore parallelism in iterative reconstruction for
to explore parallelism in iterative reconstruction for
I'd actually like to start with our key result. We're motivated by an industrial imaging application where we require performance of at least 0.6 projections per second using 400 cubed voxel reconstruction volumes. So we explore several parallelization strategies to accelerate iterative reconstruction in this context. We find that performance with several of these strategies actually meets or exceeds our minimum performance requirements across all three of our target platforms. We're quite excited about this result. I'd also like to mention the key takeaways from this talk. First, iterative reconstruction techniques are preferred, not just for our applications, but in general. Compared to the analytic reconstruction methods, iterative techniques lead to higher reconstruction quality, both in terms of contrast and resolution, and they also tend to be robust to sparse data. This is important for our application in particular. Unfortunately, iterative techniques have high computational demand. They impose both one forward projection operation and one back projection operation per iteration, which is in contrast to the single back projection operation of typical analytic methods. To overcome this limitation, then, we're going to exploit parallelism in both phases of computation. Turns out, forward projection is trivially parallel, but back projection requires more careful attention to ensure correct results. In the end, the best strategy varies with the characteristics of the underlying imaging scenario, including things like the reconstruction volume resolution, the number of available threads, and even characteristics of the underlying hardware, for example, processor frequency. However, our performance study shows that an iterative reconstruction process satisfying our application requirements is within reach. Again, several strategies that we explore provide performance that meets or exceeds our threshold requirements. Okay, in the time that remains, we'll briefly review the basis of X-ray computed tomography. We'll highlight our parallelization strategies, both for forward projection and for back projection. We'll take a look at results for our primary test platform, and we'll close with some concluding comments. So, a brief introduction. Reconstruction in X-ray computed tomography begins with a source that emits an X-ray of initial intensity I0. The X-ray passes through an object and is attenuated according to the Beer-Lambert law shown here. Finally, the attenuated intensity I1 is measured at the detector. The reconstruction process recovers the unknown attenuation coefficients, which is equivalent to computing the object's density distribution. The radon transform of the function f of xy, which here represents our unknown object in 2 dimensions, is the line integral p theta of t. Intuitively, the radon transform is the sum of values of the function f for each point, t, along a line AB through the object. The radon transform is sometimes called the ray sum. In practice, f of xy and p theta of t are functions of discrete variables. This leads to a discrete formulation of the reconstruction problem. In particular, when considered as matrices and vectors, it can be shown that vector p is the matrix product of the forward projection operator A and the vector f. This relationship, this linear system, leads to a discrete formulation of the reconstruction process shown here. F equals the matrix product of the inverse projection operator A inverse and measured values p. Direct methods for solving this system do exist, but these methods are generally impractical, in part because the inverse operator may not exist. If the inverse does exist, it may not be unique. And for reconstruction, A inverse is at the very least ill-conditioned, and this is a result of the noise that's inherent to the data acquisition process. On top of all this, matrix inversion itself is an expensive operation, even for small matrices. Alternative methods instead rely on the back projection operator, which represents the ray sums of all rays passing through any point xy. The iterative methods we consider here, as well as the analytic methods commonly used in commercial XCT systems, rely on the back projection operator as a solution to the reconstruction problem. As the name implies, iterative techniques converge to a solution by refining increasingly accurate estimates over several iterations. Iterative reconstruction includes families of both algebraic and statistical techniques, which fundamentally differ in the underlying methods used to compute and apply the estimates in each iteration of the algorithm. In this work, we focus on the algebraic reconstruction technique, or ART. We use ART because it provides an intuitive formulation in which ray sums are computed directly. Moreover, ART serves as the basis of more advanced algebraic or statistical techniques, so an implementation based on ART, like the one we use here, can be extended to leverage these more advanced techniques, if necessary. As I noted, we are motivated by applications in industrial imaging. In particular, we look to support near real-time decision-making in non-destructive testing and dimensional metrology applications. We need to compute high-quality reconstructions fast enough to guide decisions during the testing process. And for that, we need fast, high-quality reconstruction techniques. Our ultimate goal is to allow users to quickly identify features of interest and make decisions about the next testing phases based on what they're seeing. You can think of it as reconstruction in the loop for the testing procedures. As a result, we have some important performance and fidelity goals as outlined here. Notice first the reconstruction interval, 2 minutes or less. This goal supports our near real-time constraint. Also, observe that we're using only 8 to 16 projections. This constraint is due partially to the cost of running our acquisition apparatus and partially due to the physical constraints of the apparatus itself. We're interested in iterative reconstruction in part because it handles the sparse projection data better than its analytic counterparts. We also seek to reconstruct volumes up to about 1.2 cubic meters with a feature size of 3 cubic millimeters. This constraint leads to 400 cube voxel resolution volumes for our target application. It's within this context, then, that we consider ways to improve the performance of iterative reconstruction. Recall that these techniques require both a forward projection operation and one back projection operation, so we seek to parallelize both phases of computation for maximum performance. In the first phase of computation, forward projection, we accumulate ray sums along rays through each detector pixel. Forward projection has 2 critical operations. For each ray, we accumulate the values of every voxel the ray encounters, and from the perspective of each ray, this is a write operation. However, from the perspective of each voxel, this is a simple read operation. We just read the value of the voxel and accumulate it in the corresponding ray sum. As a result, forward projection is trivially parallel across rays. Multiple simultaneous read of any particular voxel value is not problematic. There are no conflicts, and we're able to maximize parallelism with the available threads. In back projection, the second phase of iterative reconstruction techniques, we smear or distribute the accumulated ray sums from forward projection, or really a correction term that's computed from those ray sum values, back across the voxels that are traversed by a ray. Like forward projection, back projection has 2 critical operations. For each ray, we read its value, and then adjust the value stored in each voxel that ray traverses according to its correction term. Thus, for each ray, we read its value, but for each voxel, we write. Because of this, naive back projection in a parallel context is problematic. The write is per voxel, and multiple simultaneous writes of any particular voxel value leads to conflicts and ultimately incorrect results. Parallel back projection thus requires a means to prevent, or to avoid, conflicting writes in order to guarantee correctness. We consider 2 possible approaches here: synchronization primitives, mutexes in particular, to prevent the conflicts, and task thread mappings to avoid conflicts in the first place. With mutexes, we serialize multiple simultaneous writes to a particular voxel value using these low-level locks. The advantage here is simplicity and correctness. However, this approach may not scale well due to contention for the per-voxel locks among the simultaneously executing rays. In the second approach, careful parallel task assignment, we instead seek to avoid conflict by construction. We guarantee conflict-free updates by ensuring no two rays within a parallel workgroup access the same voxel. This approach is both correct and potentially more scalable, no contention over the per-voxel mutexes. However, we have to be able to recoup the overhead of determining conflict-free mappings in order to realize an actual performance boost. We call the assignment strategy we consider in this work pixel spacing workgroup assignment. In this case, we compute the distance in pixel space between any two rays that pass through the same voxel for each and every voxel in the volume. We then reduce over all of the voxels to find the maximum distance of such rays. Given that distance, then, tasks can be assigned such that the distance between rays executing within each workgroup is greater than this maximum distance. In this way, we guarantee that no two rays attempt to update or to write to the same voxel. We consider three approaches for computing the maximum distance. In the first, we track the minimum and maximum pixel coordinates corresponding to rays traversing each voxel. Each voxel stores this extent, and it is updated for every ray that traverses the voxel. Simultaneous voxel value updates, once again writes to the voxel extent, are serialized via mutexes. This approach is simple, correct, and exact. Only pixel coordinates for rays actually traversing the voxel are tracked. However, we again rely on per-voxel mutexes to serialize updates across the simultaneously executing rays, so this approach may suffer from contention for the per-voxel locks. In the second approach, instead of parallelizing distance computation over rays, we instead parallelize over the voxels. In particular, we project each voxel to the detector to determine the extent of its projection. That value is stored in a lightweight per-voxel data structure, and we again max reduce to compute the final distance value. This approach is both simple and correct, but it is conservative. We project voxel corners to the detector, so the voxel may overlap pixels that are not actually traversed by a ray through the corresponding pixel centers. As a result, we potentially overestimate the maximum distance, which could impact the degree of parallelism we're able to exploit. At the same time, this approach projects every voxel in the volume, so the computation is linear in the number of volume voxels. It may not scale particularly well as a result. To address this issue in particular, we observe that for our acquisition apparatus, which is a cone beam geometry, that is, the camera's used perspective projection, the set of voxels generating the maximum pixel spacing distance necessarily incorporates at least one voxel along the edge of the reconstruction volume. So in this approach, we project only voxels along the edges of the volume, not all of the voxels. This approach is also simple, correct, and potentially more scalable. We reduce the dependence on the reconstruction volume resolution, right, the total number of voxels, by projecting only voxels along the volume edges. Nevertheless, this is a conservative approach as well, and so we may overestimate that maximum distance, which could possibly limit the parallelism available during ray traversal. Armed with these assignment strategies, then, parallel back projection with the pixel spacing workgroup assignment carefully maps tasks to workgroups. And then dispatches each workgroup to distribute ray sums to the voxels traversed by the rays through each detector pixel, ultimately providing conflict-free voxel updates. And it does so by construction. Okay, with these parallelization strategies then, let's take a look at the results of using them in our performance study. Our implementation focuses on the algebraic reconstruction technique, and we use thread-level parallelism expressed in OpenMP in our benchmarks. The strategies we explore could leverage other expressions of parallelism, maybe vector processing via SIMD operations, or even a hybrid vectorized threaded approach. But we focus on thread-level parallelism here. Also, we consider only valid combinations of the forward and back projection operations. For example, work group assignment and parallel back projection is combined with pixel spacing pre-passes in the forward projection step. For the results published in the paper, we use a sine wave phantom dataset at resolutions ranging from 100 cubed voxels to 800 cubed voxels. We also use simulated XCT projections as the input to our reconstruction pipeline. We simulate a 2 megapixel detector, we use 16 projections per iteration, and we execute 10 art iterations in each test. In the paper and the corresponding supplemental materials, we consider 3 test platforms. We're going to review the results for test platform 0 here. This machine has 2 CPUs, each with 18 cores, and thus supports 72 hardware threads total. Our code is compiled using GCC 7.3 on this machine. Our other platforms are configured similarly, but they do differ in the particular CPUs and some elements of the software environment that they provide. These systems offer fewer but higher frequency processing cores. The first has 2 3.6 GHz CPUs supporting 16 hardware threads, while the second has 2 3.5 GHz CPUs and supports only 12 hardware threads in total. Detailed results for these additional platforms are in the supplemental materials that accompany the main paper. Those supplemental results also provide details about our source code. We've released it under a liberal open source license, and the supplemental materials highlight some of the core elements. I encourage you to check out the supplemental materials when you get a chance. Okay, so 100 cubed voxels. First, recall our minimum performance threshold is about 0.6 projections per second. Right away, we have some concerns over projecting all voxels. This approach does not appear to scale particularly well, even for the low-resolution volume. Nevertheless, several strategies exceed our performance by about 2x or more, even with fewer than all threads. In this particular case, edge-only voxel projection provides the best absolute performance overall. If we double the resolution to 200 voxels in each dimension, we see that projecting all voxels simply does not scale. We are unable to recoup the overhead of projecting all voxels during back projection. As before, several strategies again exceed our performance target by 2x at least, and it's possible to do so with fewer than all threads on our test platform. Once again, edge-only voxel projection provides the best absolute performance, but we note that parallel back projection with per-voxel mutexes exhibits promising scalability in this 200 cubed voxel case. Moving up to our target volume resolution, 400 cubed voxels, we see that a few strategies exceed our performance target by a factor of 2 or more, once again with possibly fewer than all threads on our system, just as in that lower resolution case. However, parallel back projection with per-voxel mutexes provides the best absolute performance in this case, and it may in fact be a better alternative for higher resolution volumes. Finally, doubling the resolution in each dimension once again to 800 cubed voxels. Here, we are just shy of the minimum performance threshold with 36 threads, that's half of the total available on our test platform, but 72 threads provide sufficient performance to exceed our threshold using parallel back projection with per-voxel mutexes. Importantly, the trend here suggests absolute performance could improve with this strategy using more threads. Additional hardware resources might provide additional benefit if we need to support 800 cubed voxel volumes in future imaging scenarios. So, to summarize, we see that most strategies improve performance over the serial implementation, with improvements ranging from a factor of about 1.1 to well over 6, depending on the specific test parameters. Unfortunately, projecting all voxels performs poorly for the low-resolution volumes and simply does not scale to the higher resolution cases. Edge-only voxel projection may be preferred for problems involving low-resolution reconstruction volumes. It provides the best absolute performance for the 100 and 200 cube voxel volumes. But parallel back projection with per-voxel mutexes may be preferred for problems involving higher resolution reconstruction volumes. In these cases, for a fixed detector size and spatial extent, a higher resolution volume gives smaller voxels and thus smaller projected extents. This in turn leads to less contention for mutexes across the parallel rays. But it's important to note that different detector resolutions may influence the best performing strategy in both the high and low resolution cases. This exploration is left as future work. Okay, that's just about it. At this point, I just want to reiterate our main thoughts. In general, iterative reconstruction is preferred, both in our application and in other XCT applications. Iterative reconstruction tends to lead to higher quality results and is robust to noisy or sparse projections. We address the high computational demand of iterative reconstruction techniques by exploiting parallelism in both phases of computation. As we have seen, forward projection is trivially parallel, but back projection requires more careful attention in order to guarantee correct results. We explore several possible strategies to exploit parallelism, and we find that performance with several of these meets or exceeds our minimum requirements across all three of our test platforms. But the best strategy in any particular scenario varies with the problem characteristics, volume resolution, number of threads, processor frequency, and so forth. And our results can be used to guide the appropriate choice at runtime. In the end, we demonstrate several effective parallelization strategies for scalable, high-performance iterative reconstruction, in our application specifically, and in other applications using X-ray computed tomography. Finally, I'd just like to acknowledge the contributions of several collaborators to this project over the years. In particular, Jeff Amstutz, who is now at Intel, Beto Costello, who is now at Chatham Financial, and Chris Peitsch, who is now at Johns Hopkins Applied Physics Laboratory. We are also grateful to our funding sources, Intel and the U.S. Air Force. Thank you for your time. Enjoy the rest of the conference.
Your life.
Thank you, Christian, for your presentation.
Thank you, Christian, for presentation. Thank you, Christian, for
Okay, so if you are interested in doing a question, you can post your question in YouTube, in the YouTube chat, or in the Discord EGPGV channel. We are waiting just a few seconds to see.
We are waiting just a few
if there
seconds
are some
to see.
questions.
We are waiting just a few seconds to see
questions. Well, I don't see any question. So I have a question for
I don't see any question. So
Christian.
I have a question for I don't see any question. So Christian, I have a question for
So the question here is about. I mean, it was clear that you were using CPUs for computation of the methods. So have you had any thoughts about using some kind of acceleration, maybe using GPUs? Acceleration?
Right, yeah, so GPUs are the next obvious target for these methods. We haven't delved into that just yet, and of course the big concern there is the gap between kind of the number of threads we were using on the CPUs, right, around 72 at the high end for our test platform, compared to a typical GPU, which is going to support, thousands of threads in flight. And so the contention there is potentially much higher, and that may ultimately limit the scaling that we achieve with the results, or rather the techniques that we've considered for the CPUs in this paper. I think what the GPUs will allow us to do that's most exciting is to actually scale up the resolution on our detectors. And so, by simultaneously scaling both the reconstruction volume resolution and the number of detector pixels, right, we can kind of balance the fact that we're now dealing with thousands of threads as opposed to tens of threads, and achieve better scaling characteristics that way on a GPU platform. We didn't go down that path in this work, in part because, again, we're targeting a specific application, and the acquisition apparatus and the simulated results and everything kind of mimic that physical setup. But certainly that's a promising avenue of research, and something that we intend to explore here in hopefully the not too distant future.
Okay, thank you. And what about the size of the data sets? In particular, when we're thinking about acceleration, you are more limited in memory that you have in main memory systems. So
yeah, that's absolutely true. And so there again, kind of balancing that tension between the amount of memory that's available to us on an accelerator, versus kind of a more traditional host platform. We may in fact reach some limit where we're not able to scale the underlying reconstruction volume resolution much higher due to those memory constraints. But there again, we were looking for a 3mm feature size, which meant that roughly 400 cube voxels for our physical spatial extent of just over a meter. And so exploring the particular parameters that allow us to scale on a accelerated platform will be interesting.
yeah. Okay, thank you very much.
Okay, thank you.
So I think we are ready for the next speaker. She is Karen Tsai from Los Alamos National Laboratory, and she is going to talk about approaches for in-situ computation of moments in a data parallel environment.
Alright. Hello everyone, this is Karen from Los Alamos National Laboratory. Today I will be talking about the paper titled Approaches for In-situ Computation of Moments in a Data Parallel Environment. So why do we care about in-situ computation? Well, in modern supercomputers, we have exceptional computational capacity, but we're still struggling when it comes to the I/O bandwidth. For example, if we look at the image here on slide 2 depicting the Oak Ridge Titan supercomputers, we can see that we have 125 petabytes per second in computation. But as we start doing visualization or analysis on node, off node, or eventually post hoc, the number quickly falls off. For post hoc analysis, it is just 1.4 terabytes per second. With the I/O bottleneck, our goal is therefore to reduce the raw data through in-situ data processing and analysis to help with the bottleneck without sacrificing the accuracy in the region of interest for the sciences. On top of this, we have several challenges. First is integration. This is pretty straightforward in that the in-situ algorithm should be capable of running within the simulation without imposing any extra issues, which is why we will showcase integration with 2 different real-world simulations with our in-situ algorithm. Second, the algorithm should be scalable so that it can be run with a simulation on a distributed environment for data parallel computation on a large scale. For this, we have conducted scaling study and will present the result in the experiment section later. Last but not least, it should not pose significant performance load on top of the simulation, since a lot of the scientists already need to often spend days, weeks, or even months at a time for their simulation itself to finish. And we will address this during this presentation as well. Okay, so assuming we can address these challenges, how do we achieve data reduction without losing data that the scientists are interested in? Well, here is where pattern detection comes in. We have been using pattern detection in various different fields and areas. We will just apply that here as well. Given scientists' interested region, we can extract template to match for, then we could know where to reduce the data in the area that's not matched, because that's the area we're not interested in. But most pattern detection algorithms often have to look at every possible orientation of a given template, which this could cause a significant load on the performance. Like this 100-euro bill. Looking at these 100-euro bill, as a human, we can see that they should all match. But for an algorithm to determine that, it will have to check all possible orientation before it can make that determination. If we have to do this every time for every template, that will be 360 orientation in 2D and 10 million orientation in 3D, which, well, definitely tax the performance. So in developing the In-situ algorithm, we utilize the rotation invariant characteristic to avoid the performance load from checking all orientation. These characteristics are called moment invariants. Moments are projection to a function in space basis, and moment invariants are moments transformed in such a way that all instances of the function that only differ by rotation are projected onto the same point, making them rotation invariant. Similarity is then computed from and corresponds to a Euclidean distance between the template and the dataset from moments. For more details, please refer to the paper. For this paper, we have implemented and analyzed two different approaches for the data parallel computation of moment invariants: the straightforward integration and the fast Fourier transform. For the purpose of this presentation, though, we will just provide an overview of how the algorithm works without going into too much detail of how they are actually implemented. So let's look at the flowchart here. The dataset given as the example is a subset of the M-past ocean dataset that we will actually present as part of the example later. The grid is the resolution on which we wish to compute the moments on. Combining these two as the input VTK compute moments will then do all the computation and give us the output of the moments. With the moments and the pattern given VTK moment invariance will then give us a scalar field that contains a similarity value. As we have described earlier, similarity value will give us the means to determine the region of interest that we wish to preserve. And this is the general flow of our In-situ algorithm. Continuing off the example that was shown as part of the flowchart earlier, here again is the subset of M-past ocean dataset, slightly enlarged, and the upper right is the enlarged version of the image for the pattern. For ease of identifying the region of interest, we have overlaid the dataset with circles that encodes the similarity information that we have gotten from running both the VTK compute moments and the VTK moment invariance algorithm. The size of the circle is the size of the pattern when it was matched, and the center of the circle is the position of the matched pattern. The color of the circle here is the similarity value itself. So in this particular case, given the color map here, the white circle is the strongest match. So here, if we want to reduce the raw data, we will simply preserve the area that's inside the circle and then decrease the resolution everywhere else that's outside the circle. Then we will get our data reduction that way. In this part, we will talk about experiments, finally, that we have conducted for the paper. For better accuracy, the timing measurements are computed as an average of at least 10 runs with the same parameter on the same dataset, except for some of the large integration runs. All the presented timing were acquired post hoc to avoid tainting the result with runtime of the simulations. For all the experiments, the runs are conducted on NERSC Core Intel Xeon Haswell nodes. Each physical core is tasked with at most 1 MPI process. We chose 3 representative datasets to conduct our experiments on. The first dataset is shown in the top left, and it is a single time step from the impasse ocean simulation. Unlike in the previous example we have talked about, we use the whole dataset here instead of just a subset. We focus on the velocity 2D vector field in the dataset. Next is shown in the bottom left image, and it is a single time step from the YA31 asteroid ocean impact simulation. For this dataset, we focus on the temperature 3D scalar field. The third dataset is shown on the right. It is a single time step from the next cosmology simulation. Here we focus on the dark matter density 3D scalar field. That concludes the setup and the dataset explanation. Let's take a look at the results. First, the parameter study. For this presentation, we will only show the graph for the impasse ocean dataset, since all 3 datasets are representative and they display similar behavior. But if you're interested in all the other graphs, please refer to the paper in the experiment section. So let's start with the graph on the left for the grid resolution. The grid resolution are for how coarse or fine we wish to compute the moments on if we do not use the full resolution of the dataset. As we expected, the integration approach benefits from computing the moments on only a subset of original data, whereas the FFT approach remains unaffected. Now next is the order parameter. This is the order up to which the basis functions are used for building the kernel when we're computing the moments. So, as expected, the runtime of both approaches grow as we increase the order. However, the difference between the 2 approaches increases as the order increases. So given any higher order of basis function or larger dataset, the FFT approach will always outperform the integration approach. Now, the radius is used to build a stencil for the pattern matching, and as expected, the FFT approach does not get affected by the radius size, just like the grid resolution parameter. FFT approach demonstrates better performance than the integration approach in almost all the cases, although there is a case when we are working with low resolution combined with low order or low radius that the integration approach can actually outperform FFT. However, scientists are unlikely to make their simulation perform at low resolution, so FFT would be the preferred option in general. Next, we will look at the scaling study. For the scaling study, we have conducted both strong and weak scalings. Let's start with the weak scaling on the left. we can see that the integration approach increases exponentially, and FFT does better with overall lower values and a moderately slower rate of increase. Also, the reason that some of the large integration runs do not have a value is because even given a job wall time of 24 hours, they still did not finish. Thus, with realistic parameter combination, FFT offers the ability to run in more reasonable time. Notice that the FFT display a wave-like behavior. This is because FFT actually depend on the geometry of the dataset and processing group very much. In general, FFT prefers square in 2D and cube in 3D. FFT does demonstrate better weak scalability than the integration, but since FFT uses global communication for its transpose computation, it will not perform well when compared to other similar algorithms that employs nearest neighbor communication pattern. Okay, now for the strong scaling. Initially, FFT and integration both speed up as the number of processors increases, with FFT displaying slightly better rate. But in the latter half, integration flattens out, whereas FFT start going up. And this is because the integration approach's communication cost has started offsetting, and the FFT approach's communication cost has started outweighing the benefit of having more processors. Although integration has better strong scalability, the performance of FFT is still significantly better in actual runtime. So FFT will still be a more realistic option, given a real-world combination of the parameters. As we have mentioned before, it's important to make sure the in-situ algorithm can actually integrate with real-world simulation runs. So here we will talk about the two real-world in-situ integration that we did for our algorithm. First is the ECP Warback simulation that is modeling the particle accelerators. We integrated our algorithm with the simulation by utilizing the ascent infrastructure that was already built into the simulation run. It provides us with the ParaView and VTK integration interface. After the integration, we ran the simulation with our in-situ algorithm turned on. We used the pattern shown in the top left to identify the largest connected component from the match shown in the top right image. Here we can see how the vortex core branches off several times. From the image on the bottom left, which is a slice right before the split, and the image on the bottom right, which is a slice right after the split, we can indeed see that the central vortex splits into two cores. Next is the ECP Infix Exa simulation. This is modeling the bubble bed using computational fluid dynamics discrete element model. Unlike the Warback simulation though, Infix Exa does not have the ascent or catalyst integration already built in. So we build the simulation source code ourselves with VTK library directly linked in, and handle the conversion of raw data and all in-situ connection ourselves. With the integration done, we then use a step function, as shown in the left image, to identify a boundary of bubbles, because the scientists are most interested in the bubble boundaries. Then after determining where the bubble boundaries are, we can then subsample the original particle data at a coarser resolution in regions that are not bubble boundaries. We can see the difference from the image shown in the middle and the right. The middle image is the original particle dataset without any subsampling. The right image is the dataset after we have subsampled that is not identified as bubble boundaries. We gain tremendous data reduction even though the loss of information is small, since the subsample region display very homogeneous behaviors. And we have achieved our in-situ data reduction this way. Now, to conclude, we have successfully implemented the moment invariant
Yes, can you hear me?
All implementation in the distributed environment generate results identical to the serial ones up to numerical errors. All the algorithms are available within the VTK moment invariance modules. We also demonstrated acceleration through the FFT and a cross-correlation theorem, as can be seen in the result of the experiment. Note that given the global communication pattern that FFT relies on, it is not trivial that it outperforms and offers significantly better actual runtime in the distributed setting. With the experiments, we also discussed the scalability of the algorithm. We recommend the FFT approach whenever possible, but when it comes to an unstructured dataset or irregular distribution, the integration approach should still be kept in mind. With the integration of the real-world simulation in our in-situ algorithm, we demonstrated that our algorithm is definitely in-situ ready, and we showcased the benefit of in-situ data reduction through the subsampling enabled by the integration between in-situ pattern detection and the simulation, specifically through the bubble bed example. So thank you all for listening. If there are any questions, please feel free to ask during the Q&A session. Thank you again.
Thank you, Karen, for your presentation.
Thank you.
So let's wait a few seconds to see if somebody has questions. So the questions can be posted in YouTube stream or also in the Discord channel hashtag EGPGV. Okay, well, before waiting more for questions, I have one question. So looks like well at the end of the presentation, at the second part of the presentation includes some preliminary results for in-situ integration for two codes. So can you comment on preliminary scalability results of integrating your algorithm with those codes?
Yeah, so we didn't run the scalability experiment within the simulation, because actually the scalability experiments conducted purely for the reason that we believe it can be extended when you integrate it into a in-situ algorithm. Obviously, it would be nice if we can confirm that even if we integrated it into the algorithm for simulation, the result will still be the same. But with the results we have from the actual resources that we have was very limited, was the way that the integration algorithm was already taking up so much time as is. We didn't want to add the simulation time up of that when we schedule the jobs.
So a second question, maybe this is more about the libraries. So WarpX already includes some kind of in-situ infrastructure. And then you mentioned that, the other code, I just forgot the name of the other code, you needed to implement the in-situ part from scratch, right?
Yeah.
So can you comment on the usability of implementing the in-situ from scratch using Catalyst, Libsyn, or using the already in-situ infrastructure that is available in WarpX?
Like when we met in the presentation, Arco is available VTK library. So for the WarpX case, they have the Catalyst or the VTK integration interface already available. So in our case, it's pretty easy with WarpX. If we just turn on that interface, we can pull in our algorithm to run the in-situ. For the infix, it was more work because there was no in-situ interface anywhere, and it's actually, we might have been the first one who tried to add the in-situ at the time when we started working with the scientists. It's not too complicated after we found out where their actual data was being outputted whenever they save the raw data. After, because everything is handled in the VTK algorithm we have written, so we only actually needed to do the conversion of the whatever C++ structure they were using for the raw data into a structure that VTK can recognize.
Okay. So thank you. I don't see any additional questions in YouTube and anything on Discord. So thank you very much for your presentation, and thank you everybody for participating in this session, also for our speakers. And with this, we conclude this session. Thank you all.